So can everybody see can see me on the camera? No?
30 seconds, remember.
30, oh, 30 seconds. Oh, in 30 seconds you'll see me. But you can hear me now and see me in 30 seconds. So Gary tells me to have zero delay, we need to spend $1,500 a lecture. But with 30 seconds delay, it's free.
And even that was 4 or 5 seconds.
Or even that is 4 and 5 seconds. Okay. Where's that coming from? From the telephone? Even that, oh, it's through their, oh, okay, through their phone. So I think, guys, put yourselves on mute. Oh, okay. Okay, can I start, Larry, Gary?
I'm ready for you, yeah.
Okay, so let's start. So this is the first lecture, 6th of June, 2017, on physical metallurgy principles. And Puri just walked in. He's a procurement head. In fact, just a side note, Puri is working on brazing, and this first lecture would be somewhat useful, only somewhat useful. The main objective is so that I can relearn metallurgy. And one of the things is that this lecture is not just about metallurgy, it's about meaning of life and all the great things that happen in life. Right, Larry? Yeah. So this is a book on same topic by Reed Hill I bought in 1967, 50 years ago when I was 19 years old. So I have it at the back, 1967, IIT Kharagpur. And I still haven't finished this book in 50 years. So now, fast forward 50 years, this is a new book, the 4th edition of the same book by Professor Reed Hill from the University of Florida. And this is the best book in metallurgy. Nothing comes close. So we'll base the lectures on this book, but rather than start, and I want to finish the whole book. So rather than start from chapter 1, we will start from chapter 11 and then go back to chapter 1. So just to give an idea of what we'll cover, I'll just make a list of things we'll cover in this course. And basically, I've just listed the chapters. So what we'll do is, first we'll do structure of metals. That'll be chapter 1. Chapter 2 would be techniques of characterization of metals. So chapter 3 will be crystal binding. How do atoms bind themselves? Why don't they fall apart, right? So we'll talk about metallic bonding. And then things get interesting and complicated. We'll study dislocations. So this is important for mechanical properties. And then we'll study plastic deformation. How do metals deform? After plastic deformation, we'll look at grain boundaries and vacancies. So basically, defects in metals. And then we'll do annealing. What happens when you anneal metal? Chapter 8 will be phases. Phases in metals. Chapter 9 will be phase diagram. Oh, I missed a couple of chapters. Phase diagrams. So phase diagrams we'll start today. And then we'll have diffusion. So diffusion is mass transport in metals. We'll study that. Then we'll study melting and solidification. So this is important for brazing, because in brazing we do melting and solidification. And then we'll do precipitation hardening. So this is mostly in copper alloys, and then we'll go on to martensitic transformations, which is in steel. This is how you harden steel, by martensitic transformations. And then we'll get to steel, a whole chapter on steel, and then hardening of steel. And 16 will be, then we'll deal with copper and aluminum alloys. And chapter 17 will be failure analysis. So failure analysis last, because you can do failure analysis if you go through all these chapters. So it's a long sort of effort to go through all this material. Okay, so the book, the textbook is, as I mentioned, Physical Metallurgy Principles. Maybe I should write a little bigger. It's by the main author is Reed Hill, but this is the 4th edition. So he has 2 other authors who have, I think Reed Hill is probably no more, but the 4th edition is by 2 authors who have improved the book. So with that, let's get started. So the first thing I'm going to cover, I want to start off with binary phase diagrams. So phase diagrams are the most important things, most important item in metallurgy. So everything revolves around phase diagrams. So phase diagrams are like maps of alloys. When you look at a phase diagram, you understand basically the alloy behavior. So the first question is, what is a phase? Since we are going to deal with phase diagrams. So phase, if I look at the thermodynamic definition, it's macroscopically homogeneous body of matter, of say metal, since we're dealing with metals in this class. So macroscopically homogeneous. So what does that mean? So that means, suppose I have a piece of metal, let's say copper. At room temperature, it's solid. So I would say this is, we'll consider this homogeneous, macroscopically homogeneous, but it does contain grains. So I'm drawing grains in the copper. So let's say these grains. So each one of these areas is a grain. Now in each grain is a single crystal of copper. So in this, the crystal might be oriented like this. In this grain, it might be oriented like this. In this one, like so, and so on. So the orientations are different, but each one is a single crystal. So in a way, on a micro scale, it's not homogeneous, because the grain boundaries have a lot of inhomogeneity, because you have a lot of disorder, because 2 structures are coming together. So that's what a phase is. And so what kind of phases does copper have? So does copper have just one phase? Well, copper has liquid, gas, and solid phases. So it has 3 phases. Now in this class, we won't deal with gas, because if in your product copper becomes gas, you're in deep trouble. So we're not dealing with gas. Copper can become gas if you have arcing in your machine, and you don't want arcing, right? So let's look at another metal, iron. In India, we call it iron. So when I go to India and say iron, they look at me like, what's the matter with the accent? So this is Fe. So how many phases does Fe have? It has, of course, liquid, gas, let's forget that. So it has basically two phases, which are in the solid form. Body-centered cubic, we'll study what that is. Then face-centered cubic, we'll study that. Okay, let me also include liquid and gas. So iron has 4 phases, but for the longest time, people thought it has 5 phases. And then iron also goes through a ferromagnetic to paramagnetic transformation at Curie temperature. So let me not go there. But basically, metals have different phases, and we're dealing with phase diagrams. So, and I've mentioned binary phase diagram. So what do I mean by binary? By binary, I mean 2. 2 of what? So let me just write binary. So binary would be 2 elements. One has to be a metal, since we're dealing with metallurgy. The other can be a metal, or it could be sulfur, phosphorus, nitrogen. Silicon would be a semiconductor, so silicon. So a whole bunch of elements. So that's what we mean by binary. So today we'll do binary phase diagrams. And so right now, the topic at hand is brazing. So when it comes to brazing that we're dealing with today, we have the binary phase diagrams would be nickel and phosphorus. That's for BNI6. We have copper, phosphorus, and silver. That is B cup 5. Of course, this is not binary. This is ternary. But then we have binary silver and copper, and that is BAG8. So let's say these are the 2 binary alloys we're dealing with right now. Okay, so let's start with binary alloys. So let me take the simplest one. So the simplest binary phase diagram is called isomorphous phase diagram, or better still, isomorphous alloy system. So what's an alloy system? So that's a new term. So I'll define that. So let's draw a phase diagram. So phase diagram has the vertical axis as temperature, and we deal with degrees centigrade. The textbook deals with Kelvin also. I don't know why they deal with Kelvin, but some figures are in Kelvin, which is the pain. The horizontal axis is composition. So let me draw a phase diagram of nickel and copper. So at this point, we are at 100% nickel. At this point, we are at 100% copper. So this is weight percent copper going in that direction. So in metallurgy, we don't deal with atomic percent. Chemists deal with atomic percent. We deal with weight percent. So basically, a phase diagram is temperature on the vertical axis and composition on the horizontal axis. And we're dealing with a binary phase diagram. So we're dealing with nickel and copper in this case. So nickel and copper is a very useful alloy for us, because in our water cooling, we use copper tubes. But if you have an application where you want the material to be stronger, you would alloy the copper with nickel. Okay, so the phase diagram means on this, in this area, there different phases exist, right? If the temperature goes very high, the metals would vaporize, right? Then when you lower the temperature a little bit, they'll be liquid. And when you get to room temperature, you'll have solid, right? So as I mentioned earlier, let's figure about gas, because that is too troublesome for us. So between the liquid and the solid, there has to be a boundary, right? So the boundary could be like this. So this, we know, is the melting point of copper, right? Which is 1085 degrees C. I've looked at many different books. They all give different melting point of copper. In 2017, I can't get one number. So for nickel, it is 1455 C. So in between, there has to be a boundary, right? Now, the way I've drawn it is just one line, but that's not what happens. For mechanical engineers, when you deal with water system, you have ice, water, and gas. You actually have a straight line boundary between the liquid and the gas. But for some reason in metallurgy, which we will discuss soon, we don't have that. Between the liquid and the solid, we have a boundary. Actually, let me just move this little up. So the boundary is not just one line, but it's a region. So I've just moved the melting point of nickel to 1455 C. Okay, so here on the top we have liquid, here we have solid. And the solid, I'll call it alpha. So just to keep things simple, short, so the solid phase is alpha. So this region would be liquid plus alpha. So above this line, we call this line liquidus. Above the liquidus, you have liquid, and this line, since that is liquidus, this is solidus. So below the solidus, you have solid. In between, you have a mixture of liquid and solid, alpha being the solid. So I mentioned, I'll define what alloy system is. So the word system in thermodynamics, it means something else. In metallurgy, it means alloy system would be, I would call this nickel copper alloy system, meaning all the possible alloys that can form between nickel and copper, they form the nickel copper alloy system. So all these different alloys, they would comprise a system. Now, one other thing that is very important in phase diagrams is that the way I've drawn it, this is an equilibrium phase diagram. This is under equilibrium conditions. So what does equilibrium mean? So equilibrium means that we are cooling this very, very slowly. So let me take a case, let me take a composition. Let's say this composition. So this composition would be, let's say, 75% nickel, and 25% copper, right? Because I'm closer, so this is 50-50, so this is nickel rich and has less copper in it. So if I take this composition and I start off at this temperature, so here the alloy is a liquid. So we start cooling it slowly, slowly, slowly. We get to this point. At this point, we start getting, as we come down, we start getting solidification. At this point, it's completely solid. But this is under conditions of slow cooling, very, very slow cooling. If I cool fast, then I don't get the reactions happening at these temperatures. The temperatures decrease. So equilibrium conditions means very slow rate of cooling. Or if you're going from room temperature, very slow rate of heating. So that's a very important thing because when you look at phase diagrams and we think of these temperatures, we have to remind ourselves that we're dealing with very, very slow rate of heating and cooling. So we have to allow sufficient time for the reactions to happen. Now, if we were to quench an alloy, then the room temperature properties would be those of high temperature. And so let's say if I quench to this temperature, then the properties would be of that of an alloy of a higher temperature. So we have to give it time to equilibrate. And how do metals reach equilibrium? The atoms move. So there's actually atomic motion, which is thermally activated. So just as a recap, every point on this phase diagram refers to a phase. So if I deal with this point is defined by this composition and that temperature. And the phase here is alpha phase. So if I deal with a point over here, then I have liquid and solid at that point. So each region of the phase diagram refers to a phase or a combination of phases. So let's suppose we took nickel and copper, we mixed them up, we alloyed them, and we cooled it to room temperature. So let's look at the microstructure. So we have this piece of this alloy, and we look at the microstructure. So the way we look at the microstructure is we cut the alloy. Actually, we give it to Larry. Larry cuts the alloy, he polishes it, then he etches it. And then what do you see? So for this alloy, you would see I've drawn like 4 grains. So in each grain, there'll be a crystal. And these crystals are joined together at these grain boundaries. So these are grain boundaries. And each one of these is a crystal, just like the crystals you grew when you were 15 years old in your science fair, same kind of crystals. But you don't see them in the metal because you have many, many of them, and they're small. So looking at this microstructure, you would think that this is a pure metal because it has all these grains look the same. The thing is featureless except it has grain boundaries. So this isomorphous alloy system, this binary system, the microstructure looks like pure metal. You can't tell where the nickel is and the copper is. They're all mixed up. It's a solution. It's like adding sugar to water. But this alloy, this binary alloy, will be stronger than its parents, nickel and copper. So that's the whole idea of alloying. So the main reason you alloy is you get new properties, and strength is a big one. Of course, the color will be different. So nickel, copper, cupronickel doesn't look copperish, it doesn't look like nickel, and its resistivity will be higher. And it's, of course, its thermal conductivity would be lower, which you don't want. So pure metals have higher conductivity, and when you alloy them, the conductivity goes down, but the strength goes up. So isomorphous alloy systems, basically the message here is they look like pure metals. So now let's look at some details of how this alloy freezes. So I think I'll go to the center board, and I want to stay here. This way the camera doesn't have to go back and forth, and we can just stay on this board. So I want to talk about a little bit about freezing of this isomorphous copper nickel alloy. So I'll redraw the diagram. So basically we have temperature, and we have composition on the horizontal axis. So this is 100% copper, this is 100% nickel, and nickel melts at 1455 C, copper melts at 1085 C, and the diagram looks like this. So this is liquid, this is solid, and this is liquid plus solid. So let's choose a composition like so. So this is our composition of the alloy we have, and we melt it. So we're at this temperature. So then we cool it down. When we get to this point and we're cooling it slowly, we start getting solid. And then at the solidus, at the liquidus, it starts becoming solid. At the solidus is completely solid. But what if we, let's say, pay attention to this temperature, which is, let's say, 1200 C. So now we decide, let's study the alloy at that temperature and this composition. So we just stopped cooling it down, and the question comes up, in this alloy, how much liquid do you have? How much solid do you have, right? So it turns out that, okay, before I go there, let me just go over here. So when the temperature was this, the composition of the solid was this. So this is the composition of alpha, the solid, and this is the composition of the liquid. So let me call it alpha 1, liquid 1. So just at the point where the temperature was on the liquidus, the first metal to come out has this composition, and the liquid has that composition. So liquid composition is almost the same as the average alloy composition, right? Average composition of alloy. When I get to this point, this is now the composition of the solid, and this is the composition of the liquid. So notice, as we're cooling down, the copper content of the solid is increasing. See, when we went from this temperature to that temperature, the copper concentration went from here to there, right? But the liquid composition also increased. But the average composition doesn't change. That's not intuitive, right? So I have, so in my melt, I have some solid and some liquid. We're cooling both down, and both of them are gaining in copper. So go figure. But the average composition doesn't change. And the reason that can be is because the volume of the liquid is decreasing and the volume of the solid is increasing. So that's a brain teaser, right? But that's what happens. So then the question is, at this point, how much liquid do we have and how much solid do we have? So let's figure that out. So a question is, so what I'm trying to do now is to derive what we call the lever rule. So this rule tells us at any temperature within this liquid plus alpha range, in this range, how much liquid do I have and how much metal do I have. So let's call this composition C, and we'll call this alpha C2. Okay, to keep life simple, let me call this C alpha and C liquid, and I'll call this just C. C is the average composition. So let's just do mass balance. So let's suppose the weight fraction of liquid is equal to W. So W is a fraction, right? And weight fraction of alpha is 1 minus W, right? Correct? We're dealing with fractions. So total has to be 1. Okay. So W times the composition of the liquid, which is Cl. So when I say composition of liquid, I mean the copper content, because this axis is percent copper. So W, which is the fraction of liquid, plus its copper content, plus 1 minus W times the concentration of copper in the solid is C alpha, right? So W is the amount of liquid, that's the concentration of copper in the liquid. 1 minus W is a fraction of solid, and that's the composition of copper in the solid. So that has to equal to just C, right? That's the average composition. So liquid, so copper in the liquid, copper in the solid is equal to total copper, correct? So now let's collect the W term. So Cl minus C alpha times W plus C alpha is equal to C, right? So W, the weight fraction of the liquid is C minus C alpha over Cl minus C alpha, right? So let's look at this diagram over here. So I'll call this, to keep life simple, I'll call this A, and I'll call this B, and the total, we'll call it L. So C minus C alpha is A, and Cl minus C alpha is L. So the weight fraction of liquid is just A over L at that temperature. And the weight fraction of the solid is B over L. So this is called the lever rule. So at any point on this phase diagram within this region, as you're coming down this from here to there, the amount of solid is increasing, the amount of liquid is decreasing. So you can tell how much, what fraction of the material is liquid by taking A dividing by L and the amount of solid. So this is the weight fraction of alpha, and this is the weight fraction of liquid. So that's the lever rule. So now what I want to do is to discuss non-equilibrium. So far everything we discussed is cooling under equilibrium conditions. So now let me just discuss non-equilibrium cooling. So which means cooling at a fast rate. We don't allow the alloy to reach equilibrium. So let's talk about that. And how do we get the alloy into equilibrium? How slowly do we cool so the alloy is under equilibrium condition? So, I'm drawing the same diagram all over again. So this time let me draw it a little bigger. So this is a famous nickel-copper diagram. So this is 100% nickel, this is 100% copper, and this is melting point of nickel, this is melting point of copper. So it's liquid, liquid plus alpha and alpha, so 3 regions. So let's suppose that this is our composition. So this is our C average, this is the composition. So when we get to this temperature, the liquid, the solid that comes out has composition, let's say, we'll call it alpha 0, this is the first one, and this we'll call L0 for liquid composition. So let me just draw in a crucible. So let's say this is a crucible. This is ceramic crucible. And we have liquid. So we are at a temperature over here, so everything is liquid. But at this temperature, let's call it T0, that's where, because we are fast cooling. But let's assume that at this temperature, even with the fast cooling, you get some, I'll just draw one particle of composition alpha naught. So alpha naught particle, actually many solid particles freeze out, but let's only draw one. So that particle has composition alpha naught. So let me just then jump to this temperature. I'll call it T1. So we went from here to there quickly, like instantaneously. So now this composition of the solid will be alpha 1 and liquid will be L1. So I'll just draw, so this new material freezing out will have composition alpha 1, and then let me draw another one. So this is alpha 2 and this is L2. So this third one will be alpha 2, and then the last one is right here when we have complete solid, and that is composition C, right, which is this. So you have, but this doesn't make sense, right? If these compositions are less than C and this is C, the average cannot be C, right? Correct? So the mistake I've made, which we all make, is I've assumed I'm freezing under equilibrium condition. So what really happens is, so alloy doesn't freeze like I described. So what happens is, at this temperature, it is true alpha naught came out, right? At this temperature, what happens is that this is the composition of the liquid, right? And this is the composition of the solid. So now it's this liquid that is freezing. So we came here, and from here, we didn't come down here. We are now coming down over here. So this is the composition of the solid coming out over here. So basically what happens is, so let me just keep going. So then I freeze from here, and this is the composition of the solid, and this is the composition of liquid, and the liquid, we come here, and this is the composition of solid, that's the composition of liquid, and so on. So what happens is, so let's say everything solidifies over here, this curve follows like this. So instead of following this line, we're following that line. So notice that the solid that is freezing later on, so the composition of the solid keeps on increasing. So it's not like I've drawn over here. These values are much higher. And this value is probably like 90% copper. Even though the average was, let's say, 30%, because we are freezing at a very fast rate, the way we're freezing is, it is true that at this point, this is the composition of solid, but then we jump over here, that's the composition of the solid, that's the composition of liquid. But now, this is the composition of liquid, that's the composition of solid, and so we have this staircase thing going down. So the liquid composition that is freezing, it keeps on increasing. So now you can see that if you take the average, it'll come to C. So now you have this alloy which is highly segregated. You have very low copper content over here, very high copper content over here. So how do you reach equilibrium? You heat. You heat this up, and the diffusion of the atoms will bring this into equilibrium. So to achieve equilibrium conditions, the copper ions, the copper atoms have to keep diffusing into the solidified material. So you need time and temperature to cause this diffusion to happen, so that you can have a homogeneous material that follows the phase diagram. So you see, the basic message is phase diagrams are equilibrium diagrams. They are not, they are only good for very slow cooling. So I have 5 minutes left. So let me just explain how we get this phase diagram. How does one derive, how does one obtain a phase diagram? So let's suppose we start with pure nickel. So pure nickel. So this is time, and this is temperature. So I take pure nickel and I cool it down at a slow rate. Temperature will drop, right? But then at the melting point, it'll become at 1455 C, the curve will become a plateau, and then so this is liquid, and at this point is solid, so the curve goes down. So here, you know what the melting point of nickel is, right? So that's this point. So you got that point. So again, we can do the same thing for copper. If you do it for copper, you get a similar curve, and this is 1085. So you get that point. In between, let's say we have this composition, and we're cooling this alloy, what you will get is the temperature versus time plot. So you'll be cooling down, and when you get to this temperature T0, the cooling rate will slow. So this is T0. So you keep cooling down slowly. When you get to complete solid, the cooling rate slope will change. It'll increase. So this is complete solid. So you know these two temperatures. This is the liquidus. This is the solidus. So that's how you draw the phase diagram. And you can draw it for different compositions. And you can get the whole phase diagram that way. So one last thing I want to leave you with is what's called a Gibbs phase rule. So Gibbs phase rule comes in handy. And we'll study that in more detail when we do thermodynamics of alloys. So Gibbs phase rule. So Gibbs was a great guy, and Gibbs gave us the thermodynamics of stability of systems. Gibbs said that a reaction can happen if the entropy of the universe increases. So this is just a sidebar. So if you have any reaction, anything happening in this world, it'll only happen if the entropy of the system increases. It won't happen otherwise. So to make things happen, of course, when you're creating a diamond has low entropy, right? So you got to put in work. So Gibbs came up with this condition under which reactions happen. But this is a little different. This is Gibbs' phase rule. And what Gibbs' phase rule says is that P plus F is equal to C plus 1 under constant pressure. Because metallurgy is done under constant pressure, mostly 1 atmosphere, right? So all your blast furnaces, your heat treating, everything is done under constant pressure of 1 atmosphere. So P is number of phases. F is degrees of freedom. We'll explain that. C is number of components. So for our binary phase diagram, the number of components is 2, nickel and copper. So in our case, we have nickel plus copper, which is 2. We have 2 elements. So binary phase diagrams have 2 components, 2 elements. In our case, nickel and copper. So C is 2. So number of phases, degrees of freedom. So suppose you choose this point. So number of phases for this point, I'll call this point 1. Number of phases is 1, right? So we have P plus F is equal to C plus 1. So number of phases is 1. Degrees of freedom we would like to know. So C is 2. So we have F is equal to 2 for this point here. What that means is I can vary the temperature, I can vary the composition and the temperature, and I'm still in the same region. So I have 2 degrees of freedom, temperature, composition. So let's pick a point over here. Okay, let me pick a point over here. So let's call that point 2. So at point 2, my number of phases is now 2, right? Correct? And so let's see. So I have P is equal to 2 plus F is equal to 2 plus 1 is equal to 3. So my degrees of freedom is 1. So when I'm in this temperature range, my degrees of freedom is 1. What that means is I can only change one thing at a time independently. Say, okay, on this axis, I can change my composition, right? I can go along this way and nothing changes, the number of phases stays the same. And if I go vertically, if I change temperature, I get a new line. So I change my temperature, but that also changed my composition. So I can only change one thing independently. If I change the temperature, then my composition changes. So I can only make one change independently. The second change depends on the first change. So on that note, I think I'll stop. It's 2 o'clock, a little past. So that's lecture 1. Next time we'll do eutectic phase diagrams. Thank you, guys.